In this video, we shall look at a couple of review problems on Bernoulli's equation. First, a brief introduction. Assume we have a pipe that carries water between 2 points, point 1 and point 2. Now this pipe is situated above the ground in such a way that the height of point 1 is h1 from the ground and the height of point 2 is h2 from the ground. Let's assume that the speed of water at point 1 or at the cross-section 1 is v1 and the speed of water that's coming out of cross-section 2 is v2. Now let's assume that this water is not compressible, meaning its density is constant throughout the pipe. And the pressure at cross-section 1 is P1 and the pressure at cross-section 2 is P2. Bernoulli's equation relates H1, P1, V1, and ρ to P2, V2, and H2 in the following manner. It says P1 plus ρ g H1 plus half ρ V1 squared equals to P2 plus ρ g H2 plus half ρ V2 squared. That is Bernoulli's equation. What happens if the pipe is a horizontal pipe, like the one shown here? So the speed here and speed there is denoted as V1 and V2 as before, because this is cross-section 1 and this is cross-section 2. Assume the pressure here is P1, the pressure there is P2. So the density of the fluid or any liquid that's passing through this pipe is ρ. However, since the cross-section 1 is situated at the same height as cross-section 2, the following equation will not have that term. It will just cancel out because H1 equals to H2. And the Bernoulli's equation for this particular system reduces into the one shown below. P1 plus half ρ V1 squared equals P2 plus half ρ V2 squared. Now let's get to the problems. Problem 1. A liquid of density 800 kg per cubic meter flows smoothly through a horizontal pipe as shown below. A1, that is the cross-sectional area of that surface, is 1.4 times 10 to the power minus 3 meters squared, and A2, that is this cross-sectional area, is 0.7 times 10 to the power minus 3 meters squared. The pressure difference between the wide and narrow sections, that means between P1 and P2, is 4,200 pascals. Find the volume flow rate of the liquid and also the mass flow rate of the liquid. So let's write down Bernoulli's equation for the system. Since this is a horizontal pipe, the two cross-sectional areas are exactly at the same level. So the Bernoulli's equation becomes P1 plus half the density of that liquid, V1 squared, equals P2 plus half ρ, or the density of the liquid, V2 squared. We also know from equation of continuity that A1 V1 equals A2 V2, namely the flow rate in volume per second must be the same at both cross-sectional area. From this equation, we know that since A1 is larger than A2, then V1 is smaller than V2. That means pressure P1 is greater than pressure P2. This conclusion comes directly from Bernoulli's equation. So let's rearrange this equation there. P1 minus P2 equals half rho V2 squared minus half rho V1 squared. Note that from this equation of continuity, we can express V1 in terms of V2 in the following manner. A2 over A1 times V2. Since A2 is half of A1, we see that V1 becomes half of V2. Putting everything together in this equation, P1 minus P2 is the pressure difference, 4200 Pascal. So 4200 Pascal right there equals half. The density of the liquid is 800. It's given right there. Now V2 squared, we don't know what V2 is, but that's alright. V1 is half V2, so V1 squared is 1/4 V2 squared. And this equation enables us to solve for V2. And if you solve for V2, you will get 3.74 meter per second. Now we can determine the volume flow rate and also the mass flow rate. The volume flow rate is given by the product of cross-sectional area and speed at that cross-sectional area. Since we have determined V2, let's use the second cross-sectional area A2 to compute the volume flow rate as A2 times V2. A2 is 0.7 times 10 to the power minus 3 meters squared. V2 is 3.74 meter per second, and that's going to give you 2.62 times 10 to the power minus 3 cubic meter per second. So that is the volume flow rate. To determine the mass flow rate, all you have to do is to take the volume flow rate times that with density. Now, since the volume flow rate is 2.62 times 10 to the power minus 3 cubic meter per second, and the density is 800, you will get the following for the mass flow rate in kg per second, namely 2.1 kg per second. And that solves the problem. Problem 2. Figure below shows a cross-sectional view of a dam. So that is this diagram right there. The water level in the dam is 16 meters. So that is the full water level. A horizontal pipe with a radius 3 cm. So that is that pipe right there with the radius 3 cm. Passes through the dam at depth 7 meters. And then you have this plug that is denoted in red, secures the pipe opening. What is the magnitude of the frictional force between the plug and the pipe wall? So let's do that first. The idea is pretty simple. At depth 7 meters, there is water pressure that is pushing the plug rightward. In order for the plug to secure the pipe opening, there will be frictional force between the plug and the pipe wall in that direction, opposing the force from the pressure. So let's assume the frictional force is little f, and the force due to pressure is capital F. So you see that friction equals the capital F from the pressure. And the pressure that we are referring to is the pressure due to the depth difference given by little h. And we know what that pressure is. It's the density of liquid, in this case it's water, gravitational acceleration g, times little h, which we know to be 7 meters, times the cross-sectional area, which is the cross-sectional area of that opening. The cross-sectional area of the opening is the same as the cross-sectional area of that horizontal pipe. Now we can compute what that cross-sectional area is because we know the radius to be 3 cm. So that capital A is given by pi 3 cm converted into meters is 0.03 meter squared. The density of water is known to be 1000 kg per cubic meter. So substituting in here, we can compute the frictional force. which will be 194 newtons. Note that we have used the value of G of 9.81 meter per second squared in the calculation. So we record the answer for part A there. Now let's do part B. Calculate the amount of water both in cubic meter and in kg that exits the pipe in 1 hour if the plug is removed. If this plug is removed, then the water would rush out like that. We need to know what that speed is. That is the speed of water that is rushing out of that pipe opening. And here we can use Bernoulli's equation to do that. Let's assume this is part 1 and this opening is part number 2. So the pressure at 1, P1, which is atmospheric pressure, plus the term rho g h, because the water surface is at height h from, let's say, the bottom. Now this water surface can be considered to be still, so that term half rho v1 squared can be taken to be 0. So let's equate that to the terms at the opening. So the pressure there is P2, but this is also open to the atmospheric pressure, so P1 is the same as P2. They will cancel each other. Plus the term rho g altitude. The altitude here is h minus little h, so that rho g h term will be rho h capital H minus little h. And since at the opening the water is rushing out with a certain speed, we should also anticipate the term half rho v squared. You have one more cancellation. This term will cancel that term, in addition to the density canceling each other like that, and we can actually figure out the speed as 2g little h square root. Using 9.81 for little g, and we are given what that little h is, it's 7 meters. We can do this calculation and we will get the following: 11.72 meter per second for the speed of the water that's coming out from the opening. So this will enable us to calculate the volume flow rate from that opening. It is just the cross-sectional area at the opening times the V that we have just calculated. The cross-sectional area is given by pi. The radius of the opening is 3 cm, so it's 0.03 meter squared. The velocity of the speed is 11.72, and that will give you the volume flow rate 0.0331 cubic meter per second. And we can use this to answer part B. First, calculate the amount of water in cubic meter that exits the pipe in 1 hour. So from this expression we know in 1 second the amount is 0.0331 cubic meter. In 1 hour, which has 3,600 seconds, the amount in cubic meter would be 0.0331 times 3,600 cubic meter, which is about 119 cubic meter of water. And the amount in kg, let's call it m, is just the density of water times that amount in cubic meter, which is 119. The density of water is 1,000 times 119 cubic meter, which will give you 119,000 kg. And that solves the problem. Thank you for watching.